This meeting is being recorded.
In the next section of Chapter 16, we'll take a look at how these conjugated dienes can be prepared. So what we see here is we have an allylic halide here in our first example. So we can perform an elimination reaction using a sterically hindered base like our tert butoxide potassium shown here. And we can do that elimination and form our second pi bond here. So we already had one to start, and we formed a second. So this is one type of reaction that could be used using this allylic halide with a sterically hindered base to form a diene, like shown. The reason that we use that sterically hindered base is to prevent a substitution reaction from occurring. So we know that SN2 would be in competition with our elimination reactions here. So we want the elimination to occur. In our second type of reaction that we could see form a diene would be with a dihalide, and we would use a similar bulky base, such as this tert butoxide potassium again, and we could do two subsequent eliminations and form this same product, this 1,3-butadiene. So let's take a look at this next section. We'll also talk about some properties of these dienes and how they relate to other single bonds. So when a single bond is part of a conjugated pi system, they're going to be shorter than a typical single bond. So what we see here, the explanation shown below, is that each of these carbons involved in our single bond are sp2 hybridized versus these two carbons in this single bond, which will be sp3 hybridized. So we know that an increase in s character would make these orbitals closer to the nucleus of the carbon, and pulling in those electrons a little bit tighter, having that more s character, would make these sp2 hybridized carbons in this diene a little bit more stable. So again, versus the sp3 hybridized carbons that have that more p character, and that overlap would be a longer bond overall. So we know that we have the shorter with the more s character in these dienes than in a typical single bond, which has more p character, so they're a little bit longer. And that is further explained here, right? The shorter the orbital, the shorter the sigma bonds will be. So that's what we see between our sp3 in that like ethane single bond that we saw on the previous slide versus our diene that had those sp2 hybridized orbitals. So the increase in s character causes the shorter bonds. So what about the stability of these conjugated dienes? We see that down below we have our energy diagram showing the heats of hydrogenation. So when we add hydrogen to break these double bonds here, and we see that over here as well with the diene, you may expect that a 1-butene, if we combusted 2 moles, or rather we hydrogenated 2 moles of 1-butene, we would expect that to be the same energy difference as if we hydrogenated a 1,3-butadiene, since they both have the same butane final product here. But actually what we see is that there's about 15 kilojoules per mole more stable of a compound here with the diene. When the two pi bonds are conjugated, that increases our stability. So what we see then with the 1-butene is that it exists at a higher potential energy than our conjugated system. So our diene here is about 15 kilojoules per mole more stable, is one way that we could look at that. So let's take a look at these structures here and see if we could rank them in order of increasing stability. So let's take a look at compound A here. This will be our lowest, so we'll say this is number 1. This is the least stable, so we'll note that here. And there's a combination of reasons why we can make this determination due to the degree of unsaturation, the degree of conjugation, and also the degree of alkene substitution. For all of those reasons, we would find that compound A would be the least stable. It has no conjugated pi bonds. Then we can move to, well, compounds B and C here. These are pretty similar. We're going to rank C as our second highest here, or second lowest rather, and then B would be a little bit more stable. You really don't have to make a full determination between the two here as far as alkene substitution goes, but we should note that we do now have some conjugated pi bonds here in both of these structures. So these are pretty similar, but let's take a look at D, which will be our most stable compound. And again, we have a conjugated pi system here, and then we have another conjugated pi system here. So that is why we can determine structure, our D rather here, to be our most stable. So we would rank these 1, 2, 3, 4 in this order. So we know that sigma bonds are generally free to rotate, depending on large bulky groups sometimes prevent that. But for the most part, we have these sigma bonds that allow free bond rotation. So when we talk about our butadiene specifically, we have what results as the S-cis or the S-trans conformations due to this rotation on the carbon-2, carbon-3 single bond. So the two most stable rotational conformations we should note are the cis and the trans. We'll look at one other conformation that is least stable out of these three. And the reasoning behind it is shown down below. So we have the S-cis conformation shown here, where we have that conjugated system there. And then we also see that conjugated system of our overlap of p orbitals with the S-trans conformation as well. The only difference is that this we would say has about a 0 dihedral angle, and then this here has about a 180-degree dihedral angle between our pi bonds. So let's take a look at this another way. The S-trans is going to be the lowest energy conformation overall because of the lack of steric hindrance. So we see those two pi bonds separated about 180 degrees between them, and versus our cis S-cis conformation here, which has that 0 dihedral angle. Again, this is due to that orientation across that single bond here, and we would say that these two double bonds are in a cis relationship to one another versus that single bond, whereas these two double bonds are in a trans relationship about that single bond. So that's where the S comes from, around the sigma. So that third conformation, that would be somewhere up top. This results when we have lack of conjugation between our pi bonds, and we see that this form, when we have about a 90-degree dihedral angle, would be about 15 kilojoules per mole unstable compared to our cis, and about 27 kilojoules per mole less stable than our S-trans conformation. So that is everything from this section, and we'll continue with section 16.3 in the next video.